Yeah. Right. Good. Good morning, my dear boys and good morning, my dear students. Right. Good morning to all of you. Right. Shall we start discussion today? Very good. Sufficient strength I have come. No, it's okay. No problem. For today class, what I'm going to start a fifth unit today. Right. So the fifth unit topic is principal stresses and strain. Right. Strains. Okay. Good. This is I'm going to discuss with you in the fifth unit. A very interesting and simple thing with you. Right. Uh, Now I am projecting the Bansal textbook because I have gone through both the Punmiya and Bansal. In Bansal, it is nicely written. Okay, it's easy to follow when compared with the Punmiya. That's why I have preferred to teach you by from Bansal. Moreover, here very simply only principal stress and strains. Only the topic discussed. Actually, strictly speaking, last semester you had a subject called Basics of Solid Mechanics. In that, we should have taught well this principal stresses and mole circle. Okay, since two teachers were handling the subject and shared the syllabus and teaching, later I realized that, understand that the principal stresses, that is the only topic missing, not well discussed with you. Okay, not much discussed with you, right? So I once again teach you the principal stresses. What is going to be principal stresses? Okay, first I have to discuss with you stresses, and then the strain. Once you know the stress, you know stress divided by Young's modulus will give you the strain. Then the discussion of principal strain is easy for you, right? Because last semester mainly focused on stresses, principal stresses and principal planes and all. This semester in your syllabus you have principal strains. That too for three-dimensional, okay, and the other failure theory, right? I will tell you in a simple word before going to start the theory. I will tell you in a simplified way. This way, say you all know how to determine stress, okay? When a body is subjected to when body is subject to an external loading, okay, either push or pull loading, you know how to compute the stress induced in that body. How do you compute? Suppose you have a column. The column is subject to axial compression. How do you compute the stress induced? Once you know the axial force acting on it, the compressive force acting on it, that divided by area of cross section. Which area of cross section? Perpendicular area of cross section. You will take into account the area of the section perpendicular to the direction of loading. Okay, the load is acting axially on a column. Axis of the column is there. In the direction, the load is acting axial compression. A column is subject to axial compression. Okay, we call it as uniaxial loading. Okay, in only one direction. The member is subjected to load or force in only one direction. We call it as uniaxial loading, right? If you want to determine the stress induced in the material, what you will do? Load acting on it and divided by area. Which area? Perpendicular area, perpendicular plane. You will consider the plane which is perpendicular to the direction of loading. That area you will substitute and compute the stress induced in the material of the body, compressive stress induced in the material of the body. Okay, you are very so far you know how to compute stress this way, right? Only this much only you know. Is it whether stress induced in the body, is it uniform in all the direction? If you ask me, no. Okay, only the stress you computed in the direction of loading. You have computed stress which are acting in the direction of loading. Load divided by perpendicular cross section you have put. Okay, now the stress tensors are acting perpendicular on the plane. Okay, perpendicular plane, on the perpendicular plane in the direction of the loading. They are acting in the direction of the loading. Only that stress. In the same material, you take some other direction. Okay, there are so infinite number of directions. No, you take any other direction. Whether the stress intensity is same in the direction, if you ask me, no. Okay, the stress intensity varies. It is common sense. Understand easily. You can realize it or visualize it. The stress intensity differs. Suppose if you want to compute the stress in some oblique plane, okay, the plane is not perpendicular to the direction of loading. It is oblique. Okay, inclined plane or oblique plane. In that, definitely the stress intensity will be different. Moreover, that plane will not have only normal stress, because the direction of stress also will be acting some direction. No, that can be resolved into two direction. One is normal to that plane. You consider any oblique plane in the column. But just now I told you an example. No, in that column, in that oblique plane, the stress acting can be resolved in two well-known directions, which are perpendicular to the plane and tangential to that plane. Accordingly, the plane will be having tangential stress and perpendicular stress, called normal stress. So in any oblique plane, you will be having normal stress as well as tangential or shear stress. Okay, normal stress or shear stress, otherwise tangential stress will be acting in a plane. Okay, if just the oblique plane, you are slightly inclined. Okay, you have a plane perpendicular to the direction of loading. Lightly just keep on rotate that plane, that perpendicular plane, make it oblique. Okay, keep on rotate. The stress intensity accordingly keep on varying. Okay, the normal stress intensity as well as the tangential stress intensity. At a particular position, at one position, what will happen? The normal stress value will become zero. Only maximum shear stress will be acting in that plane. Okay, that is called pure shear. That is called pure shear. The plane will be having a particular location of the plane, a particular orientation of the plane will be having only shear stress. Normal stress will not be there. That stress is called pure shear. Okay. Now the perpendicular plane you are considering subject to only normal stress, isn't it? The plane which is perpendicular to the direction of loading is subject to only normal stress. That plane is in that plane the shear stress is zero. So if a plane is free from shear stress, we call that stress as principal stress. Okay. So the what you are computing P by A in the usual way is nothing but principal stresses. They are principal stresses. In that plane doesn't have any shear stress. It has only normal stress. Suppose in a body, in any plane, only normal stress alone act. Okay, without any shear stress, tangential stress, without any shear or tangential stress, that plane is said to be principal plane. The stresses acting in that plane is said to be principal stresses. Okay, that's what some brief introduction I have given. Now we are going to see in a theoretical way all those things. In this unit, I am going to discuss with you that one. And then once you know how to compute this, moreover, a determination of those stresses in any oblique plane, analytical way, we develop some expression. They are called a transformation equation. Transform. Okay, it's transform the stress value, no, in some other plane. That is why they are called a transformation equation. That we are going to get for the several cases. Okay, and then next I am going to discuss with you, and then resulting strain, right? So stresses plane has normal stress, shear stress. Some plane has only shear stress. Another plane has only normal stress. Likewise, we are doing computing. For that, we are developing transformation equation, and then we are computing the stresses acting in some other inclined plane, oblique plane. This process and all called as stress analysis. Okay, so this topic is called appropriate to call it as stress analysis. Okay, so once you analyze it for stress, you can compute strain, because stress divided by Young's modulus value will give you the strain. Okay, so strain analysis, principal strains you can determine, and so on. Please keep it in mind, in any body, the failure of that material will happen if any of this value exceeds its permissible value, its failure value. For example, you take a body, we can do stress analysis in that body. A body which may be subjected to only uniaxial loading, for example, your column in a building, or a body which may be subjected to biaxial loading. Uniaxial loading means loading in only in x direction. Biaxial loading means loading in x and y direction. Okay, for example, a plate analysis, you take slab in our building. When you load it transversely, it is subject to membrane action, say bending action, membrane action. Okay, so it's a plate. Slab is a plate. Okay, it has two direction. There is the x and y direction. There are two directions. So we call it as biaxial loading. That slab is subject to biaxial loading, and although it is loaded transversely, the membrane action transfers that load into in the x and y direction of the slab. Biaxial loading. Suppose you take any body which is subject to pressure. Okay, kept in a fluid, right, in water. There are hydrostatic pressure, no? Such bodies are subject to triaxial loading. Loading is acting in all the three directions, X, Y, and Z direction. Okay, accordingly, it is subjected, right? Now, if you take any point in the body, just now I told you, at one direction, in that body, there is a plane which is called principal plane, in which principal stresses are acting, maximum principal stress is acting, and minimum principal stresses are also acting. There are two planes, okay, major principal plane, minor principal plane. Major principal plane, maximum normal stress will be acting. Minor principal plane, lesser normal stress will be acting. There is a plane which is called pure shear plane in that body, in which maximum shear stress will be acting. Okay, and also we also can compute strains in it. So either the principal stress or principal the shear stress or principal strain or shear strain, any of these values reaches the failure value of that material, the particular material, the body will fail. For failure analysis, that's why it is called a failure analysis. For failure analysis, it is not necessary that the body has to fail only by principal stress alone. It may fail by if the principal stress of the material, because the body which we are dealing are not, all bodies are not isotropic material. There are homogeneous material body. For example, you take wood, or you take, for example, concrete. Concrete is very good in compression, but very weak in tension. If you push it, it withstands more load. If you pull it, it fails. For example, you take wood. Wood has got a compressive strength parallel to its grains is very high. When you apply the load perpendicular to its grains, the compressive strength is low. Okay, its compressive strength is low. Like that, since all bodies are not isotropic, but many materials are homogeneous. We are assumed to be homogeneous. Strictly speaking, they are not homogeneous at all. When concrete is a heterogeneous material, but we are assuming it as at least homogeneous. This kind of stress analysis is required. Then once you have done stress analysis, it means once you computed located the principal plane in that material, in that body, okay, and then once you compute the stresses induced in that material, once you compute the strain developed in that material, the maximum shear stress, that is pure shear, the resulting shear strain, and principal stresses and corresponding strains, everything, if you do compute, that is called stress analysis. Okay, if you do it, we can able to do failure analysis of the material, at how the material will likely to fail, in what mode the material will fail, which value will attain its failure value, which of these values, just now I told you, principal stresses, principal plane, the strains, shear stress, pure shear stress, pure shear strain, so many things are there in it. No, if any of this value attains the failure value of the material likely to fail because of that reason, right? So that is called failure analysis. So in this fifth unit, full you are going to see this only, stress analysis and failure analysis. Okay, just I briefed in a very simplified way. Okay, still I have not gone into the theory. It may confuse, you may get confused if straight away gone into the theory. If you go into theory now, it may confuse you, right? Now you have got some idea from my discussion so far, what I have told you. Okay, now you see, right? Now I am coming to that. Actually, in the Punmiya textbook, that is available. Pure that is strains, principal strains, and that too triaxial set of strains, and its analysis is available in detail in that Punmiya. But in Bansal, it is not available. Put together, principal stresses and strains put together, chapter available. But in Punmiya book, both are separate chapters. Principal stresses, and principal stresses separate. Principal strains discussion is separate chapter. Okay, first let me to brief this one. Later we will go to that. Okay, I may go a little bit speed. No problem. Just listen. Principal planes and principal stresses. The principal plane means what? Which have no shear stress are known as principal planes. The planes which have no shear stress are known as principal planes. Hence, principal planes are the planes of zero shear stress. Okay, these planes carry only normal stresses. Keep it in mind. Okay. So all of you mute your mic. Okay. Now, what is mean by principal planes? Which have no shear stress are known as principal planes. Hence, principal planes are the planes of zero shear stress. These planes carry only normal stresses. Okay, the normal stresses acting on a principal plane are known as principal stresses. Beautiful explanation, very simple, lucid language, very simple explanation is available for principal planes and principal stresses. Very good. Next, method of determination of these principal stresses. Method of determination of stresses. Not first, we are not discussing principal stresses. In general, method of determining stresses on oblique section. Okay, plane which are not perpendicular to the direction of loading. Some oblique plane. Okay, how to determine? There are two methods. One is analytical method, another is graphical. The graphical method is called Morse circle. Okay, Morse circle, that we will see later. First, I will discuss the analytical method, that is transformation equation. How to obtain the transformation equation we are going to see here, analytical method. So, analytical method for determining stresses on oblique section, that is the topic. Now, we are taking a member subject to a direct stress in one plane. Okay, direct stress in one plane means uniaxial loading. A member subject to uniaxial loading. You know how to compute the load. The stress along x direction is P by E. Okay, perpendicular to the area of cross section, which is perpendicular to the line of action of the force P. Okay, so P by E, you know how to determine a plane which is perpendicular to the direction of loading. How to compute stress, you know very well. Already you are thorough. Very good. That is P by E. You know that. Now we are considering a body. Okay, a rectangular element in a body. Okay, in a strained body, I have taken a rectangular element. It is subject to uniaxial loading P. Okay, and there is a plane. Here it is given as EF. Okay, which is perpendicular to the direction of loading. You know how to get the stress on this P divided by area of cross section. EF, the area EF will give you. Just assume time being the thickness of the element perpendicular to the plane of the monitor. Okay, is unity. Okay, just imagine the thickness of this element perpendicular to your monitor is unity. Perpendicular to the paper in the textbook is unity. Okay, please all of you imagine this element is a infinitesimal element in a strained body. At a point, just at a point in a strained body, I have taken an element. For visualization purpose, I have drawn this much big here. Okay, it is subject to pulling action here. Right? This is a perpendicular plane. This is some oblique plane, FG, which makes angle theta with the perpendicular plane here. Okay. So the other things are given. The same figure, EF, FG. Okay. And okay, we will come to that later if required. So you know the stress equal to force by area EF. Okay. That you know P by A. Next, what we have written here in this triangle, I want stress in this FG. Okay, in the EFG, in this triangle EFG, EF, okay, EF divided by FG, right? Adjacent side divided by hypotenuse is equal to cos theta. That's what written here. Therefore, FG equal to EF by cos theta. FG equal to area of the section. Area of the section FG is equal to EF divided by cos theta into 1. Why 1? Member is having unit thickness. Okay. So area of section FG is equal to this FG, this length into perpendicular to the monitor is unity. Time being just assume. That is 1. Okay. That's why this area of cross section here is FG. Area of cross section is EF. Okay. Now in this right angle triangle, you have written EF by FG equal to cos theta. Therefore, FG equal to EF by cos theta. So A by cos theta. So the area of this inclined plane is nothing but this area divided by cos theta. The perpendicular area is A, say A. The oblique area is A by cos theta. How we have got it? We have assumed perpendicular to the monitor, unity thickness, and then we have taken this length and this right angle triangle, we have written this from the, okay, A cos theta. Now, stress on the section FG. What is the stress FG on the section FG? Which is equal to the force required to be resolved. Okay. Force divided by area of FG, P by A by cos theta. So P by A cos theta. Stress on the section FG. Stress on the section FG is equal to force divided by area of the section. So the force is P, we know. Area of the section is A by cos theta, so PA by cos theta, so which is equal to sigma by cos theta. P by A, say, call it as sigma. Sigma by sigma into cos theta. Okay, this way again. This stress on the section EG is parallel to the axis of the member. Please remember, this stress on the section FG is parallel to the axis of the member. That is, the stress is along x direction. Okay, this stress may be resolved in, okay, now in this oblique plane, the stress is acting the direction of the force. Okay, this may be resolved into normal to the inclined plane and tangential to the inclined plane. That's what. Okay, we have to determine that. I will just a little bit go speedily. Okay, the stress on the FG is parallel to the axis of the member. This stress may be resolved into two components. One component will be normal to the section FG, whereas the sine component will be along the section FG. We call it as a tangential or shear stress. Okay, so how do you get it? Therefore, let them as sigma suffix n. Okay, what is this person has done? He resolved the force first. Okay, P and PT. P and PT means P. The axial force is resolved into normal to the inclined plane and tangential to the inclined plane. Let sigma n and sigma t is the normal stress along the section FG, and sigma suffix t is equal to tangential stress in FG. Okay, these are the notation. Remember, Pn means the axial force normal to the inclined plane. PT means the axial force tangential to the inclined plane. Sigma n means the stress acting normal to the inclined plane. Sigma t means tangential stress, stress acting tangential to the inclined plane, or shear stress acting on the inclined plane. Okay, that's what the notation adopted. Let us see what has been done. Okay, therefore the normal stress and tangential stresses across the section FG. FG is the inclined oblique section, inclined section, are obtained as normal stress is equal to force normal to section FG divided by area of the section FG. Force normal to the section FG is Pn divided by area of the section FG equal to A by cos theta. Okay, so if you resolve P, it becomes P cos theta. Listen here, refer this figure. P is acting like this. Okay, if you want to resolve this one, normal to this one. Okay, please see here, this angle is theta, this angle also theta. Remember, because this is perpendicular to the incline. This is perpendicular to the this direction of the loading. Angle between perpendicular and inclined is theta. So angle between, otherwise I can say angle between vertical and inclined is theta. Therefore, angle between horizontal and this inclined, the incline which is perpendicular to the incline. This is the previous incline. This is perpendicular to that. Okay, this is theta. This is theta, and this is also theta. Okay, so this P is acting like this. If I want to resolve perpendicular to this incline FG, it is P cos theta. If you apply your mind, you will understand. Okay, so Pn is P cos theta. That's what written here. If I am doing it on the board, and I can explain nicely. But please, later you go through these notes, the textbook, all of you having the soft copy of Benzal, later go through and apply your mind and understand, study leisurely and understand. Okay, that's what written here. P cos theta, P by A cos theta into cos theta is there already. So P by A cos square theta. So sigma cos square theta. Therefore, the normal stress sigma n is equal to sigma cos square theta. This is called transformation equation. Simple. There are so many cases. Okay, for this case, it is a transformation equation. There are other cases. Body subject to biaxial state of stress, that too like state of stress, and a triaxial state of stress. For every cases, we can get this kind of transformation equation. Okay, this is uniaxial state of loading. For this is the transformation equation. Sigma n is equal to sigma cos square theta. Please remember, the textbooks, everything written elaborately. Force normal to the section FG by area of section and all for understanding purpose. But you have to prepare notes. You have to. You need not explain, elaborate. Okay. During exam, if you want to work out any problem, if you want to do any derivation, this is simple elementary level case. There are other cases which I am going to discuss later, right? That time you should have the practice, the way of writing, the way of presenting. Another way I would say way of presenting. You should not write in not only in my subject, in any subject, whatever subject you have this semester, in all these subjects, don't try to write as it is the textbook. Okay, you have to just write briefly, write everything, because textbooks are written for elaborate purpose, explanatory purpose. But during exam, you have to present only the necessary steps in a brisk way or a simplified way. Okay, for that you should develop your own way of presenting things. Okay, so the everything ability only. We grown like that only. Do you think that somebody has done spoon feeding for me? No. Some teacher came and taught really out of self-interest. Really have to thank those teachers. Some teacher never come to class. Those teachers also liked by many students, right? But what happened? Okay, that was the important meeting. That's why it's okay, good. Because after your class, I have a PhD snaps meeting of VAT. I am the doctor committee member for a scholar there. So I received a call from former head of A-Star Lab, Advanced Seismic Testing Research Laboratory Lab, Dr. Professor Muttumani, who is the former head of that laboratory. Presently, he is the professor in VAT Chennai. One of his PhD scholar, I am the doctor committee member. So he just now he called me to for his synopsis meeting of the candidate at 11 o'clock. Very good. It's a very advanced topics in which I am the doctoral committee member. I feel proud of it. Okay, many people in our college doesn't know the value of all the such things. They have been thinking that they are very brilliant and they have been doing very great things in the Pondicherry Engineering College. It's okay. It's being recorded, no problem. It doesn't matter, right? So I will present it. Few minutes. Yeah, I hope I am audible, right? I hope I am audible, right? So I told you sigma
Yes,
cos
sir.
theta. Yeah. Next tangential stress is equal to now the force acting tangential to that in oblique plane, inclined plane, divided by area of cross section of that plane. Okay. So that is here. This is the direction of the force acting. Okay, you have to resolve it tangential to this one, which is theta here. If you resolve it tangential to this one, it becomes sine theta. Okay, P sine theta. So that is why easy to follow. Only it is written such that very big discussion. Okay, no, nothing. It's very simple. Tangential. So P sine theta by the area of cross section of the oblique plane, which is A by cos theta. Therefore, P by A sine theta cos theta you are getting, which is equal to P by A is nothing but sigma sine theta cos theta. This can be written as sigma by 2. Just you multiply this by 2. Sigma by 2, okay, into 2 sin theta cos theta, you can write it. All right, 2 get cancelled. No, that's why. Instead of writing sigma sin theta cos theta, you can write sigma by 2 into 2 sin theta cos theta. 2 sin theta cos theta is nothing but sin 2 theta. Sigma by 2 into sin 2 theta. Since 2 sin theta cos theta is equal to sin 2 theta. Okay, this way we can write in a very, how to say, in a compact form manner. Sigma t equal to sigma by 2 into sin 2 theta. This is the transformation equation. Okay, so using this, you can determine the tangential stress, the shear stress acting in a oblique plane. Okay, because theta keep on varying. We are rotating the oblique plane. Just okay, imagine. So the angle made by the oblique plane with the perpendicular plane is theta. Okay, it's keep on increasing. Can rotate it. That's why this equation is called transformation equation. Okay, so using that you can determine tangential stress as well as normal stress acting in any other oblique plane. Okay, remember this one. You have to put it in a box. Sigma t is equal to, you have to put it in a box here. Here sigma n equal to, you have to put it in a box and you have to memorize this. Sigma cos square theta, here sigma by 2 sin 2 theta, right? So this way. What is the other discussion? Now the discussion is like this. From the equation 3.2, 3.2 means which one? This transformation equation, okay? Sigma n is equal to sigma cos square theta. That is the transformation equation. It is seen that the normal stress sigma n on a section FB will be maximum, right? Actually, this normal stress will be maximum when cos square theta is maximum or cos theta is maximum. And cos theta will be maximum when theta equal to 0 degree, isn't it? Because cos theta 0 degree is equal to 1. But when theta equal to 0 degree, the section FG will be coincide with the section EF, the perpendicular section. Okay, the oblique section FG will coincide with section EF means the perpendicular section. Okay, but the section EF is normal to the line of acting of the loading. This means the plane normal to the axis of loading will carry the maximum normal stress. Okay, maximum normal stress is equal to sigma cos square theta. Sigma equal to cos square 0, because cos square theta maximum value is, you have to put theta equal to 0. Is equal to sigma, nothing but sigma. So that is called principal stress. Okay. So from the equation, it is observed that the transition stress, shear stress across the section FG will be maximum. Okay, the next discussion has come. Okay. So here the maximum shear stress is, the maximum normal stress is here in this plane, EF only. The plane which is perpendicular to the direction of loading. Okay. Only this plane has maximum normal stress. It has only normal stress. Okay. No shear stress. That's why the stress acting on this plane is called a principal stress in this case, in this uniaxial state case. Biaxial state case, it may differ. We will see later. Okay. That's what. The discussion. Next, the next discussion is which plane has maximum shear stress. That discussion is there. From equation 3.3, the signed equation. This is a transformation equation for shear stress. That is tangential stress. Okay. So from equation 3.3, it is observed that the tangential stress, that is the shear stress across the section FG will be maximum when sin 2 theta is maximum, and sin 2 theta will be maximum when sin 2 theta value is equal to 1 or 2 theta is equal to 90 degree or 270 degree. Okay, it means if the 2 theta value is 90 degree, the sin 2 theta value will become 1, or 270 degree it becomes 1. Therefore, 2 theta equal to 45 degree or 135 degree. This means the stresses will be maximum on two planes inclined at 45 degree and 135 degree to the normal section EF as shown in figure. Okay, the value of maximum shear stress equal to sigma by 2 into sin 2 theta. This transformation equation, no, in this you substitute sin 2 theta equal to 1. Okay, there was sigma by 2. So the maximum shear stress value is sigma by 2. Okay, which plane carries that one? Which plane has that one? The plane which is one plane is the plane which makes 45 degree with the given plane, with the perpendicular plane EF. Okay, a plane which makes 45 degree means this one. The plane makes 45 degree here, and then from this 135 degree. Okay, here another plane perpendicular to that. The plane which has makes 135 degree to the perpendicular plane here will be having maximum shear stress. Two planes contains maximum shear stress whose intensity value is sigma by 2. This is applicable only for this case, uniaxial state of stress case. Okay, that you have to remember. There are other cases that we are going to see, right? That is a discussion in that. Using this, we can work out some problem. Yeah, it is shown here. It's well shown here. This is the perpendicular plane. The plane perpendicular to the direction of loading. This plane, okay, which makes 45 degree with the perpendicular plane, will be having first plane of maximum shear stress. Okay, theta equal to 45 degree. Next, another plane from here 135 degree. Another plane which makes 135 degree. Okay, this also sine plane of maximum shear stress. Theta equal to 135 degree. So two planes which are perpendicular to each other. Okay, carries maximum shear stress whose value is sigma by 2. Okay, the simple stress analysis we have done for uniaxial state of case. There is a sign method discussed that is not necessary. Okay, because first method we have seen by resolving the force. In this method, they have resolved the stress. Okay, either we can tell that way or this way, no problem. I will skip this, not necessary this one. In other way discussion also, given for this. Okay. Other way discussion also given for the discussion we have done so far and completed. Same thing again, once again explained in another way. Right. So using this elementary concept, the simple uniaxial rate of stress, we can solve some elementary problem, 2 marks questions. Okay. Let's see one such question. Yeah, I will finish. I am going to finish off. Another 10 minutes. I am going to finish up. Okay. A rectangular bar of cross section area 10,000 mm square is subjected to an axial load of 20 kilonewton. Determine the normal and shear stresses which is inclined at an enema. Anybody wants to say anything? Screen not visible. Oh, இவ்வளவு கட்சி சொல்றீங்களா? முன்னாடி நம்ம இடையில கட்டாச்சுன்னா ஷேர் பண்ணிருக்கணும். வெரி குட், வெரி குட்மா, வெரி குட்மா. ஏமா என்கிட்ட ஃப்ரீயா பேசலாமா? ஏன் பயப்படுறீங்க? 1 minute. ஆமாம்மா, ஆக்சுவலாக வாட் ஹேப்பண்ட் இன் பிட்வீன் ஐ ரிசீவ்ட் a phone call, no? So the internet disconnected, again got connected. So in that screen sharing will go. Again, you should have reminded me for sharing the screen. Okay, yeah. Now it is visible to you, no? Yeah, now it is visible. Am I right? Yes.
Yes, sir.
Yes, yes. Very good, very good. Yeah. So we can solve such a elementary level problem here. Okay. So please see here, a rectangular bar of cross section area 10,000 mm square is subjected to an axial load of 20 kilonewton. Determine the normal and shear stresses on a section which is inclined at an angle 30 degree with the normal cross section of the bar. Okay, please all of you remember what I am discussing is what I am discussing with you now are supposed to be discussed, should have been discussed last semester. Okay, that only the topic was missing last semester, right? Now that's why I'm again teaching you now, right? But in your syllabus, you have whatever I'm discussing, it's continuity only you have in your syllabus. No problem. First you should understand this, then only you can understand some elementary level problem. If you do it, you can understand the what is necessary to work out such a problem now to enhance the level of understanding of the concept. Okay, so that's why we are working out. It is very elementary level problem, but elaborately it is written. This much elaboration not required. You know what is that? Sigma n normal stress is equal to, straight away you can start from here, sigma by cos square theta. Substitute sigma n is equal to sigma cos square theta. Sigma already computed, p by a. Sigma is equal to p by a, already computed. P is given, a is given. P by a is found to be 2 Newton per square. Simply 2 into cos square 30 degree. Oblique the angle made, oblique plane angle also given 30 degree. Simply substitute, you are getting 1.5 Newton per square. Okay, sigma n normal stress acting in the oblique plane is determined. Again, using the transformation equation, at tangential stress sigma t is equal to sigma by 2 into sin 2 theta. Sigma already computed. Substitute. So this way we are computing the normal stress, sorry, tangential stress, the shear stress. Sigma t means tangential stress or shear stress is found to be 0.866 Newton per square found. Okay, you do that straight away directly. You write the formula, substitute the data and compute. This much explanation not necessary. This is for textbook, no, reference book. Understanding purpose, it is written in a well elaborate manner. But in the exam, you have to, it's a 2 mark question only. Simply you have to compute. Write the transformation equation, substitute the data and compute. That's all. What is the next problem? Find the diameter of a circular bar which is subject to an axial pull of 160 kilonewton. If the maximum allowable shear stress on any section is 65 Newton per square, it is a value. The maximum allowable shear stress is supposed to be 65. You should not exceed. In that bar, which plane will be containing maximum shear stress? Obviously, the plane which makes 45 degree with the perpendicular plane. Okay, we know the concept now. There's a plane which makes either 45 or 135 degree with the then a perpendicular plane will be having maximum shear stress. What is its value? Its value is sigma by 2. That also you know. Maximum shear stress value is sigma by 2. This all those things you have studied. That is why in this problem, what the author has done, he computed the stress first, P by A. Okay. In that D is unknown. The diameter of the bar is unknown. For area, pi by 4 D square. D he kept as unknown. Okay. P is given. Everything is substituted. Now, the maximum stress is given by maximum stress intensity, you know, sigma by 2, which is equal to this much. Okay. This sigma by 2 should not exceed 65. It is given. Okay. The maximum stresses should not exceed 65, right? So sigma you have computed in which d is unknown. Now what is sigma by 2? Maximum stress is sigma by 2. Sigma by 2 is this divided by 2. Okay, this divided by 2. That is computed. Now this is equated to 65 now. Okay, because this is nothing but the shear, maximum shear stress. Okay, this value and all you know. We are equating that to the allowable shear stress here, which is 65. From this we are computing D. Thus we determined what should be the diameter of the bar. That is determined. Okay, in this problem. That's what determined. D equal to 39.58 mm. With this I will finish. Time is almost over. I will finish. A rectangular bar of cross section area 11,000 mm square is subject to tensile load P as shown in figure. The permissible normal and shear stresses on the oblique plane BC are given as 7 Newton per mm square and 3.5 Newton per mm square respectively. Determine the safe value of P. It's another problem. Okay, here you ask to determine the axial pull here, the value of P. Only the permissible stresses, the normal stress should not exceed 7 and the shear stress should not exceed 3.5. Likewise, it is given. Where will we be having a maximum normal stress? The plane which is perpendicular to the direction of loading, you will be having maximum normal stress. What is value? P by A. That you know. Okay. What about maximum shear stress? Maximum shear stress is nothing but sigma by 2. Okay. That value should not exceed 3.5. Okay. So in this problem, what they have done? They computed sigma. What is that? Sigma n. Okay. Maximum normal stress is computed here. Sigma cos square theta. Okay. Say the sigma value is safe stress in the member. So sigma n equal to sigma cos square theta or 7 equal to sigma cos square 30 degree. Therefore, sigma equal to this one. Okay, from this they got sigma. Using equation 3.3. Okay, since cos is 30 degree, because the oblique plane is given, no? Yeah, where is that? The permissible normal and shear stresses on the oblique plane BC are given. Okay, the plane is given plane. Okay, which is the angle is given as 60 degree. It means this plane makes 30 degree with the perpendicular plane. This plane makes 30 degree with the perpendicular plane. So theta value is 30 degree here, right? What is the theta value? The angle made by the oblique plane with the perpendicular plane. Okay, that is 30 degree. That's why it is written here like this. Sigma is nothing but the safe stress in the member because it should not exceed 7 Newton per meter square. It is given. Okay, so that is substituted. Sigma n equal to sigma cos square theta or 7. The normal stress should not exceed 7. No, that's why 7 equal to sigma cos square theta. From this, the sigma is computed, which is found to be 9.334 Newton per meter square. And then using equation 3.3, transition stress equal to sigma by 2 sin theta, sin 2 theta. Sigma t value is given. It should not exceed. Shear stress should not exceed 3.5. No. So substitute 3.5 sigma by 2 sin theta into 30 degree. From this, the sigma is once again computed, right? Out of this 2 sigma value, you have to take the least one. Okay. The safe stress is the least of the 2, 8.083 Newton per square. Safe value of the axial pull is equal to safe stress into area of the cross section. So area of the cross section is given. This into this will give you the safe load. Okay. So I just fastly I told you something. You apply your mind, go through later this problem and understand. Likewise, the other problems are there. Since time is over, I will do one thing. I will stop it here. Okay. Because 11 o'clock I have another commitment. Biax state of stress. Oh, only one more problem. Only one problem left. Let me to finish that one. What is this? Yeah, another problem. Okay. Another problem is, yeah, a similar problem, I think. Another problem. What is another problem? This is the last problem in this case. The wooden piece, 10 centimeter by 10 centimeter in cross section, are glued together along line AB as shown in figure. Okay. Are glued together along line AB as shown in figure. What maximum axial force P can be applied if the allowable shearing stress along AB is 1.2 Newton per meter square? Okay, it is given here. The AB plane, oblique plane is given 30 degree. Therefore, what is the angle? What is the theta value? The angle made by this oblique plane with the perpendicular plane is 60 degree. Theta value is 60 degree here. It is 100% similar to that of previous problem. Only thing is this one. So theta value is 60 degree. Sigma t equal to 1.2. It is given. Okay. Next, what is here? Yeah, it's over, no? So therefore, sigma t equal to sigma by 2 sine 2 theta. So 1.2 is equal to this much, right? From this, sigma is found to be this much. Therefore, maximum axial force equal to P equal to the stress in the direction of P into area of the cross section. Stress into whatever stress you computed, normal stress, that into area of cross section will give you the safe axial pull. Okay. So if you apply this much force, the shear stress induced will not exceed the permissible value. That's the meaning of it. We'll see, we completed. Next class, we will see this case. Please here, see here, the previous problem, both permissible value for both normal stress and tangential stresses were given. That is why we computed the normal stress two times, and we have taken the least value. In this problem, only the permissible value for tangential stress alone given. That is why only once, only for shear stress sigma t, sigma by 2 into sine 2 theta. In that we have substituted, okay, and we got the stress value, normal stress value, that into area of cross section gave us the maximum permissible load, the axial pull, safe axial pull that can be applied on this body is determined. Okay, please later you go through the Bansal soft copy textbook is available with you. Go through. Why I am in hurry now? We have to concentrate much on the continuity of this. These are the introduction. Okay, speaking, this and all should have been discussed last semester. That is the only thing we didn't discuss in detail last semester. That's why I am discussing it now. After discussing this these cases, now we have discussed only uniaxial state of stress case. Next, I am going to discuss with you biaxial case here, as shown here. Okay, a member subject to like direct stresses into mutually perpendicular direction. This case is a sine case. I will discuss it in the next class. Now I want to record your names. Okay, just let me to record your names. Yes, your names have been recorded. Okay, so I have recorded your name. Please, all of you remember, we are in 5th unit now. I can finish off your 5th unit. Okay, the only left out topic is in your 4th unit, unsymmetrical bending. Still, I have not discussed unsymmetrical bending of your 4th unit. First, let me to finish this 5th unit. Afterwards, I will teach you the unsymmetrical bending in 4th unit. With that, your syllabus will be over. This 5th unit will take another 3 classes to complete. Okay. Another 3 classes to complete, 3 or 4 classes it may take to complete for syllabus for you. I will try to finish well before the 31st December. I will try to finish. Okay. So first I will stop recording. If you want to discuss anything, you can discuss later.